So I've had a couple of people come to me and say, hey, I took some data, I tried to run it through the tracker, but it came back saying it was going to take 14 hours, or maybe it was going to take 3 days to process the data. Well, clearly, that's way too long. It should never take that amount of time to process the data, so something is wrong. Now, one possibility is maybe they have a low-end graphics card that's simply not up to par. But the other possibility is that they simply acquired this data in a fashion such that it is not optimized for synthetic tracking. So I'd like to go over some slides that I put together. These are some tips and ideas on how you can improve your data collection so that you can improve your chances of asteroid discovery or even just confirmation of asteroids. So let's go ahead and get started here. The first tip is choose the right setup, choose the right tool. So if your goal is to discover new asteroids, then you really want to have a wide field of view. That's number one, it's the most important thing. So even if you had a gigantic 8-meter telescope, it's not going to do you any good if you're looking through a straw. So you really want to have that wide field of view, but you do want to have some aperture. So the two of those together translate into having a fast focal ratio. F2, maybe F3. So the Rowe Ackerman Schmidt astrograph, the new RASA telescopes, those are going to be perfect for this application. Now, I've also had some success with a wide field refractor. So even though it didn't have a whole lot of aperture, I believe it was 127 millimeter aperture, the wide field of view makes it really great at discovering new asteroids because you just have so much of the sky you're looking at a given time. And so the short focal length in conjunction with the right pixel size makes it a nice wide field of view. Now, plate scale, that could be up to 3 arc seconds per pixel, so you could be undersampled. Again, the goal here is simply to discover a new object. So you're not trying to get really accurate measurements, just enough that you can say, hey, I found an object here in these images, and I found it again over here, and so forth, and I was able to compute a rough idea of its orbit, enough to the point where I can follow it up. So now once you are trying to do confirmation, if that's your goal, and maybe that's all you do, maybe you don't care about discovery, then you can have a narrow field of view. In other words, maybe you're trying to confirm really faint asteroids, so maybe you do need a huge amount of aperture. Typically those larger instruments have longer focal length, so they're going to have naturally a smaller field of view. And that's okay when you're trying to just do confirmation. In this case, because you are trying to get good measurements, you want to have a better plate scale, so I say around 1 arc second per pixel is pretty good for that. So now you've taken some data and you want to run it through the tracker, but you don't want to get back a whole bunch of false detections, or you want to make sure that when there is a true object in that field that it gets ranked number 1. So the first step here is a flat field, and what I mean by that is you have consistent brightness throughout the image, but also from one image to the next. And the reason this is important is that the tracker computes a quality value for each detection, and the way that's computed is in part it looks at the consistency and brightness of the object from one frame to the next. So if on frame number 1 the object is really bright, and on frame number 2 it becomes really faint, really dark, that's going to impact the quality score. So that's why you want to have a normalized background level, and the software has a way to easily achieve that, but I'm just pointing it out here that it is important to get good results. The next thing is you want to remove artifacts. So even though they may appear to be stationary, these hot pixels, defective columns, when you align the images, they then appear to be moving objects. Well, clearly that's going to be an issue if your goal is to look for moving objects in the first place. So you want to try to get rid of those. If you're not able to fully do that for some reason, then you can try dithering, but I almost never use dithering. But if you do, my suggestion would be to not be overly aggressive with it. So anyway, like flat fielding, the software has tools to get rid of those hot pixels and defective columns, so it really shouldn't be too much of an issue. The third tip here is software binning. So in other words, if you're not able to achieve a desired plate scale natively with your sensor, then or if someone hands you some data and it's not the plate scale you want it, you can use the software to bin the data. And again, it depends on what kind of plate scale you'd want to achieve. If you're searching for asteroids, let's say you're at 1 second per pixel native, you want to go to 2, then that's going to do a bin 2 by 2. So now you're able to reduce file sizes by a factor of 4 and processing time by a factor of 4. So that's really helpful. So again, if you're trying to search for objects, you can easily get away with that 2 arcsecond per pixel and dramatically reduce processing time. So again, as I mentioned at the beginning of this video, processing time, some people have an issue with that, and this is where binning to achieve a certain plate scale can be very helpful. Now, on the other hand, if you're just trying to confirm asteroids, processing time is not a huge issue because you already have a good idea of the motion of the asteroid. So you don't need to do a full blind search. You don't need to search all possible speeds and all possible position angles. You already have some idea of the motion of the object. So processing time is not an issue because you can put limits. You can specify a range of speed and a range of position angle. So again, you're trying to confirm an asteroid, you're trying to get good measurements of it, so go ahead and stick with the 1 arcsecond per pixel resolution. The next tip is optimal exposure time. So this is important. If you have too long of an exposure, the moving object is going to cause a streak, it's going to cause trailing loss. What that means is that now you have reduced the signal to noise ratio on that object. So you don't want that. You want to choose an exposure where you have minimized the streak, but you also don't need too short of an exposure. Again, it just partly depends on the speed of the object. So for the purpose of discovery, most near-Earth objects are discovered between 0.5 arcseconds per minute to 10. So you're looking at a bell curve. You say 95% of objects typically have those kinds of speeds at the time they are discovered. Now, it's not too terribly uncommon for it to go up to 30, maybe 60 even, but it's just less and less likely. There are some that, of course, they've made it pass by, and that now they're faster than the apparent speed of a satellite. So maybe they're going, again, that's geostationary satellite is 900 arcseconds per minute. So that's all possible, but the likelihood of discovering it at that is simply not as probable. But anyway, the point is, as an example, if you have 2 arcseconds per pixel resolution and you're permitting a streak of 4 pixels, then you could take a 48-second long exposure. Now, if you want to be able to detect up to 30 arcseconds per minute, then as an example, you would choose 16-second sub-exposures. So these are all things that can be computed ahead of time, and you basically just say, yeah, I'm going to run a survey, and this is what I'm going to use as my exposure time, and rarely do you change it after that, but you could. Maybe you have an array of telescopes, and you've said, okay, I want these telescopes to be optimized for this speed of object, and maybe I want these telescopes to be optimized for the slower objects, so you could do that as well. Now, if the goal is to confirm asteroids, then, well, you already kind of have an idea of the motion, the speed of the object, so use a calculator, or better yet, maybe you've compiled a table, a lookup table, that says, well, my plate scale is this, the speed of the object is between this and this, therefore I should use this duration sub-exposure. That's another way to do it. So most of the objects on the NEO-CP page, the NEO confirmation page on the Planet Sensor website, they can be very faint, so they benefit from having longer sub-exposures. But still, I say don't go much beyond 5 minutes. Try to keep it 5 minutes or shorter, just because there is an advantage to having more and shorter sub-exposures to a point. Alright, this last tip here, tip number 5, is minimize the gaps between exposures. So this does play into the processing time. Now the tracker can handle gaps. It can do it. There's no issue. If you've taken some exposures and then you decided to, for whatever reason, stop the acquisition, and then you've got some more exposures, it'll handle that just fine. The problem is that now you've increased the total duration. So gaps cause an increase in the total duration on that field. Longer duration means that an object covers more distance, which means there are going to be more search vectors, and that ultimately means the processing time increases. So you have to search in both dimensions. You have to search both horizontally and vertically, so both x and y axes. And as a result of that, the processing time increases by the square with the distance covered. So that's why gaps are detrimental to processing time. So even though you can still get results with gaps in the data, you can handle them, you're going to dramatically increase processing time when those gaps are large relative to the sub-exposure time. So here are some examples. So example A, we're taking 30-second long exposures, and we have a 2-second gap between them. We're taking 50 of these exposures. The total duration is 1600 seconds. Now, that's going to result in a total number of vectors of 121,969. And that's not bad. That's actually kind of good. If you process that many search vectors, that's kind of typical. And so not a huge issue there. Now on the other hand, let's suppose we have, again, 30-second exposures, but now we've introduced an increase in the gaps between them. So for whatever reason, maybe the camera can't download very quickly, or for some odd reason, we have these large gaps between exposures. So now there's 60-second long gaps, same number of exposures, but much larger gaps. Well, now the total duration is 4,500 seconds. So we've increased total duration by a factor of 2.81. However, the total vectors has gone up to almost 1 million. So 964,800 vectors. And that's an increase by a factor of 7.91. So that's huge. And again, the reason for that is distance in both dimensions. So you square it. So 2.81 squared is, so it's almost a factor of 8 increase. So that's why you don't want to have really large gaps if possible. Now, and that's relative to the sub-exposure time. So if you have a 5-minute long exposure, then maybe a 60-second gap isn't so bad. The reason for that is that when you have a long sub-exposure time, Tycho, the tracker, is going to think, well, you're not searching for a very fast object, therefore it will not move, it will not cover as much distance. So I put together a spreadsheet, and that's part of the demonstration here. I've made it available where you can try out some different inputs and see how long it will take to process a given set of data based on those inputs. So let's go ahead and take a look at that. Okay, so this is the spreadsheet. As you can see, this is processing time Excel spreadsheet that I put together. It's broken into 2 sections. So the first is input, second is output. So input is where you define parameters pertaining to the data acquisition, and then output is a result of computing the total processing time based on those parameters. It also computes a ratio of processing time to acquisition time. So in this example, it took 3.6 hours to acquire the data, and that's specified here. So 13,000 seconds to acquire the data, and that includes the gaps between exposures. and then the total processing time was 2.2 hours. So you might say, well, 2 hours is a long time to process data. Well, in the context of it took 3.6 hours to acquire the data in the first place, 2 hours is not so bad. Now, if we were on the other extreme where we had really short exposures and it took 5 minutes to acquire the data, and then obviously 2 hours would be way too long. So this calculator, the spreadsheet, gives you a way to look at these parameters. So again, for this example, what I did here is I took 60 exposures, and they're actually 3 minutes in duration. Each of them are 3 minutes. And so obviously I'm not optimized to detect the really fast moving objects, but I can still, I put an upper limit of 3 arc seconds per minute. So as I can still detect some near Earth objects just fine. And especially since I have an undersampled plate scale, what that does for me is that a moving object will occupy that same pixel for a longer period of time before causing a streak, before it causes trailing loss, which again is a degradation in signal noise ratio. So this is another example where being undersampled is a good thing for discovery. In other words, it permits you to detect faster moving objects with a given exposure time. So going through this example, again, 60 exposures, total duration 217 minutes, so that's the 3.6 hours. They are 4096 by 4096 pixels, so have a nice wide field of view with this plate scale. So that's 3 by 3 degrees, very nice field of view. So if we look at the track navigator, these are the results, and what we're interested in here is the metadata, so we can view that, and this basically gives us some information on the processing speed. So you'll notice this is the parameter in the spreadsheet for processing speed. So you can plug that in. This is in terms of vector pixels per hour. So I just copied that out from here. So 4.7 E13, and as you can see, the 8,000 seconds, that's just how long it took to process the data. So that's the 2.2 hours. Now, one thing you'll notice is that it says that number of vectors is 103,968. So again, the spreadsheet is kind of an estimation. So normally default granularity is 0.67. That's something that you can specify in the tracker, and I actually used a granularity of 0.8. Again, you can see that in the metadata here. So this is 80%, so 0.8. But when I use that value here, again, the estimation in the spreadsheet thinks that we're going to have total number of vectors adjusted as 267,000. And so, again, the reason this is an estimation is because it doesn't actually have access to the image data. So when the tracker computes the vectors to explore, it's able to say, well, okay, given a certain upper limit on object speed, it could move X amount of pixels. And based on that maximum movement, then it tries to say, well, what would be the relevant motion vectors to explore without oversampling on the vector space itself. So in other words, you don't need to stack all of the images in such a way that you've got 0.1 pixel of shift from one motion vector to the next, for example. I'm not going to go into all the details on that, but suffice to say, the granularity adjustment that you put in here is probably not going to be the same that you see here. It's going to wind up being whatever would yield the adjusted number of vectors. So I'm going into a lot of detail here, but the whole point of this is, again, it's an estimation where you would ideally say, well, let's suppose we had our 30-second exposures. Again, I'm kind of going back to the example here in the slideshow where we had 30-second exposures, 2-second gaps. So I'm saying, and we have, oh, I don't know, the 2 arc seconds per pixel. Anyway, if you plug in, 2 arc seconds per pixel. So if you plug in some values here, again, that was 1600 seconds for the 2-second gap. Then you can kind of get an idea as to how long the processing time might take. And based on number of images, that was 50 images. So it's telling us for this graphics card that I have, we're running at that speed. And again, that's also dependent on sensitivity setting as well. So the more sensitive you run the detector, then the processing speed will be somewhat reduced as it spends more time. Anyway, again, it is just a spreadsheet that makes an estimation, but it's good for comparing values. So it might have taken you 2 hours if you had the 2-second gap between exposures, but then if you raised it to 4,500 seconds because you now have the 60-second gap, well, now it would take 17 hours. So that right there is kind of a good way to see the impact of gaps between exposures. So again, a 2-second gap, we had 1600 seconds and total processing time of 2 hours, but then we said, well, we're gonna, for some odd reason, have 60-second gaps. Then now we have 17 hours of processing time, which is indeed quite ridiculous. So again, you can play with it and see what values you get. Oh, and by the way, if you were to do binning, then you dramatically cut down the processing time, of course. So we were 2 hours, and then now we're half an hour of processing time, just by adjusting the plate scale, effective plate scale. So okay, anyway, I hope this gives some insight onto how processing time works with the tracker, and how you might optimize your data set. Again, the key rule here is to gaps are fine, but you do want them to be small in relation to the sub-exposure time. So, well, thanks for watching, and see you next time.